to LinkedIn and YouTube. All right, we are live on YouTube. All right, and it will just take 1 second for us to, perfect, we are now live on LinkedIn. Excellent. Welcome, everyone. Michael, are you ready to get started here?
Yeah, definitely. Hi, everybody.
Perfect. I will kick things off by welcoming everyone today to our brand new series, Delta Lake Deep Dives. My name is Carly Akerley, and I am a communications manager at the Linux Foundation. This new series is created for the community to dive deeper into more technical topics surrounding Delta Lake. So thank you so much for joining us and being part of our first ever session. I'm very excited to introduce our first guest, Michael Shtelma, the lead specialist solutions architect at Databricks. Michael is based in Germany, so it's a little bit later for him, and has extensive experience helping companies implement LLM applications using open source technologies like PyTorch or Hugging Face and other applications. Today, Michael will be focusing on the integration of Delta Lake and PyTorch, bridging the gap between these two powerful tools. In this session, you will learn how to leverage the best of both worlds, Delta Lake's robust data management capabilities, along with PyTorch flexibility and efficiency in deep learning training. We're sure you're going to have a lot of questions here from Michael. So as he begins his presentation, whether you're joining us from Zoom, YouTube, or LinkedIn, please drop your questions in the chat. We will address those at the end, ensuring you leave here with clarity and some new knowledge. Without further ado, I will pass things over to Michael to get things started. And Michael, the virtual stage is yours.
Awesome. Thanks, Carly. Hi, everyone. So today we will be talking about scaling deep learning using Delta Lake storage format and PyTorch. And of course, we will do all that on Databricks. So let's get started. At first, we will talk a bit about the typical deep learning projects, and we will see how it usually looks like and what challenges people do have while implementing like standard deep learning projects. And after that, we will talk about sharing data sets among different projects. So that's what we see in the bigger organizations where they work with bigger data sets, and then they have multiple teams training multiple different models using the same data sets or maybe some derivatives of it. And then we will talk about DeltaTorch, what it is, and why we actually need a new tool for that. We will talk a little bit about the architecture, and after that, I will show you a couple of demos, like a really standard vision demo, and after that, we will also see how we can do something more interesting like stable diffusion, and how you can integrate DeltaTorch into different applications. Okay, so let's get started. So how the typical deep learning projects looks like? Usually, we start with the raw data. We ingest our raw data into the bronze layer. We can have some data pre-processing done by the ETL team, but after that, we have to build our features. We have to maybe build embeddings. So we have some more specific data pre-processing, which is specific to our vision project, or we have data pre-processing specific to our, for example, NLP projects, where we can maybe already pre-tokenize our data. We can also clean it and do different things. But as a result of this data prep project, we should have the clean data set, which is directly available for the training, and we can directly use it with PyTorch. Okay, and after that, we can actually implement our deep learning model. We can train it, and after we train, we will have to evaluate it, of course. And if it's okay, then we can go to the deployment. Or maybe if it's not okay, we will iterate around data preprocessing and training and evaluation a bit. And now let's see how all that changes if we have, like if our data set is used by different teams. So let's assume that we have a data set with, like, let's say it's a vision data set with some images, and we are building the classification model, just trying to make something up to make it simple. And we have multiple teams which are using the same data set, maybe with some additional fields available there, and they're building different classification models. So what is going to happen in that case? So in that case, we might get different update schedules. So our data might be ingested at different schedules, right? So the updates to our data. And we might have a lot of additional features, and not all the features are used by all the teams at the same time. So there might be a subset of features which are used by the first team, and there might be a bit different subset of features which is used by another team. So we might have multiple pictures, or we might have multiple derivative features and things like that. And of course, since we have talked about updates, when we start a project, and when we train our model, usually we don't want to have the updates into the dataset. So usually, at least during the development phase, we would like to stick to some version of it. And we don't want to see those updates, which, for example, can be ingested on a daily or weekly basis. So those are the challenges when we are starting to kind of looking at into the bigger picture, and we have multiple teams or multiple deep learning projects running on the same set of data. And now let's see the challenges that we get if we introduce simultaneous updates into those into our data set. If we have if we're introducing different updates at the same time at first, the first really simple challenge which might arise if we just do it in the same time, we might run into, let's say, we just can corrupt our data. And with the big data format, that's happening quite often. And if we, like, let's say, try to solve it by just copying the data set and basically make one data set available for each team, like not the data set, but the copy of this data set, we can definitely do that as well. But it might be prohibitively expensive because we are going to copy, in that case, like a lot of data, and that's not always a nice solution. Another problem is, of course, that we can introduce not only the data duplication, we can introduce, for example, some old features, or we can still be using some data which in reality should have been deleted, or like we might just run into really different issues. And of course, the size matters as well. If you have a big data set, at first it's quite hard to make the copies. It's also hard to process it, like basically to do the data pre-processing all the time if we do those copies. And as I mentioned before, we don't need all the features all the time. We also don't need all the rows all the time. So different teams might be using a different subset of features, subset of rows. So we will have to allow filtering during the training. And that's usually also, it's not easy to do. Okay, so now let's come up with the requirements for the shared dataset. What do we need to have in order to easily use the same dataset with multiple deep learning projects? At first, we need efficient loading of the subset of features. We also need basic filtering on the row level and also on the column level. We also need versioning. As I mentioned before, we want to fix our version of the data during the development phase of the project because we don't want to run into different metrics values during the development, and those changes might be just introduced by an update, right? And after we do an update, we get a different version. And all that should be available without creating a new copy of our data, right? So we don't want to have a copies. We want to use the data as it was ingested and processed directly for training. So let's now discuss how we can achieve that. I think the most obvious approach would be just to store our data on our files on the hard drive, but that means that basically we will have to run our machine forever, which is hardly acceptable. Another approach would be just to store our data in cloud in the form of JPEGs or PNGs for the vision data set. We can use JSON-L for the text. That's definitely going to work, but there are a bunch of drawbacks. At first, we will have to load it from cloud all the time. Maybe we'll have to even copy it before we start the training. It's pretty easy to do the filtering, of course, if you have the right metadata, but still we'll have a lot of small objects in cloud, and it's going to be basically we will have to send a request for each file. So it's going to be hard to get right performance with such a setup without copying the data to our local SSD first. And of course, we have things like TF records. So we have special formats like TF records and or web datasets. That might be a good solution. But the thing is that in that case, we will not be able to use that data for anything else. And that's usually a challenge. Usually, we would like to have a data set available for other applications, maybe for applications which do not support those special formats. And if you would like to use one data set for everything, including training and other things, it should we should not use something that specific as TF record. And of course, there is another approach. We can use an open format like Parquet, a very well-known big data format for that. And Parquet is a columnar format. We have efficient loading for, we can easily load subset of columns. We can easily do the row filtering because we have row groups and we have statistics. So basically, we can do pretty much everything we wanted. And we can easily store Parquet in cloud, and we can load one file at a time. So we have pretty efficient loading. But there are a couple of drawbacks. At first, there is no versioning. And so we will not be able to version it in the right way without doing a full copy. And also there is no direct support for transactions. So why it's important? Because if we are having multiple ingestions during the week, we might run into issues. So we will our writer processes might corrupt the data, and if we get updates, it's going to be quite hard. The writer process might corrupt our data set, and by doing updates, I think the chances to corrupt the data is even higher. So it's not an actual that's not an actual solution for our problem. And now I'd like to introduce Delta Lake storage format because it has all the benefits that Parquet has. Delta Lake is just a metadata layer on top of the Parquet, but it brings a lot of really nice features on top of the Parquet. So with Delta Lake, we have performance because we have a lot of nice features on top of the Parquet, which allows us to easily read data. We also have the full support for the AC transactions on the dataset level. So with AC transactions, our write-up processes, our ingestion processes are not going to corrupt the data and are not going to interfere with long-running training. We also have versioning. So now we can version our data. And for example, our hero run can just use one version of the data, and it will not see any new transactions, any new ingestion. And the same applies for the project itself. We can fix the version during the project, for the project phase or for the sprint, and we can use one version until we make a conscious decision to update and to use another version. And there are a lot of other features available. And Delta Lake is an open source format backed by the Linux Foundation. You can easily use it anywhere you want. So now let's discuss how we can use Delta Lake with PyTorch training. A couple of features of Delta Lake, which I'd like to mention in addition. At first, as I mentioned, it brings performance because we have data skipping and we have the ordering. Data skipping means that in Delta Lake we have statistics, and for each file we know what is maximum and minimum of our for each field or feature. So we can automatically skip files we don't need, and we have the ordering which allows us to place similar records together. Then we can also unify with Delta Lake batch and streaming. So we can ingest the data during training, and we can also have a streaming ingest, for example, and it will not affect our reader process like our training process. So we have full versioning, so we can easily access earlier versions of our dataset, and we can reduce I/O using data skipping, and we can easily integrate all that with PyTorch using DeltaTorch, because without DeltaTorch there are no direct support. And another disclaimer, there is another interesting project, I think a well-known project, which is called Petastorm. And I think a lot of people might just ask the question, why do we need something new? Does it make sense just to use Petastorm directly? So theoretically, it's possible because Delta Lake is based on Parquet. So theoretically, you can use Delta Lake API to understand which Parquet files you actually need, and you can use Petastorm directly. But there are a lot of caveats. At first, it's a workaround. So you will need to understand Delta format to understand which Parquet files you actually need. So you will need to parse the transaction logs and things like that. And another issue is that with Petastorm, you're not going to get really nice performance. And another issue is that the memory footprint that Petastorm has in reality is quite high. I will show you later the performance comparison, and you will see that actually with DeltaTorch, you can have a way better performance. Okay, so I have mentioned it already a couple of times, but what we are talking now about is the new open source project called DeltaTorch. It's part of the Delta incubator, and it allows you to easily use Delta Lake tables for training with PyTorch. And what it does, it just creates a PyTorch data loader for you. And after that, you can just plug it into your existing deep learning training script, and you can just directly use it. And it can also be used with distributed training. So you can use DDP, PyTorch DDP, or you can use FSDP with the data, like with DeltaTorch backed data loader. And in addition to that, it will automatically handle sharding of your data. And it means that each worker process, like each rank, will see own portion of the data. But let's now see how you can actually use it. There are a couple of requirements which your data set will need to fulfill in order to use DeltaTorch. So your Delta table will need an ID field. And this ID field should be an auto incrementing field. So it should just start from 1 and go up And why we need this field? We need this field because DeltaTorch is using it to actually shard the data. So when we doing distributed training, we can use this field to calculate which portion of the data each rank will need to use. Okay, now let's see how you can actually use it. At first, you will need to install it, and for that you can just do pip install DeltaTorch. Of course, you can pip install it from the GitHub repo, but now we also have it in PyPy repo. And after that, you can just use one method. Like there is one method which is important, and pretty much you don't need anything else. You can just call the create PyTorch data loader method, and you can pass the path to your Delta table. And it can be a DBFS path if you are on Databricks. It can be direct, like an S3 path, or ADLS, like path to ADLS Gen 2 container. And after that, there are a bunch of fields you will need to specify. So at first, you will need to specify the name of the ID field. So that's our auto increment field. And you will need to specify the field specification for all the features. And in the current example, which you can see on your screen, we have two features. First one is an image. And this image is just a binary field, which contains a serialized image. And we can tell DeltaTorch to use pill to load this image, and then we can apply transform. And transform, it's a standard PyTorch transform that you are already, like you might be already using. So you don't need to re-implement it. You can use your existing transforms. But during the demo, we will look into that in more detail. And we have another field which is called label, and that's a simple field which we can directly use. And since both Parquet and Delta have schema, we know the type of those fields. So your data will have the right type, and you don't have to actually really think about it. So what else do you need to specify? You will have to specify number of workers. You can specify if you would like to shuffle the data, and you will have to specify the batch size. Of course, those things, you don't need to specify them. They have reasonable defaults. Basically, you can just omit them. And after that, you get the you get the data loader, and you can just iterate over the data loader, right? Now let's remember our specification or our requirements, which we have defined before. So we also said that in reality, we need filtering, we need versioning, and we need a couple of others. So since Delta Lake supports versioning, we can easily integrate it here. So we can just say version equals 8. So it means that our data, data loader will be seeing the 8th version of our data. So you can easily fix your version, and you can also make it part of your configuration setting. And in addition to that, we have also said that you might have multiple teams using the same data set, but in reality, they're using different subsets of our data set. So you can use partition filter. In order to really have filtering, you will need to partition your data set, and you can directly use your partition columns as a filter. That's a limitation. So you can have multiple partition filters, but you can use only the partition columns as a filter. So that's a limitation, of course, but it's something that allows us to have a really good performance and still have a filtering. So as you see, we both support filtering and versioning. And now let's look into the whole architecture. So that's how your whole architecture with DeltaTorch can look like. We have our source data sets. Then you use Spark to do the data pre-processing. And as a result, you just write out your master data set as a Delta Lake. And after that, you can have multiple training processes which are leveraging the same master data set with different features, with different subsets of the data to train different PyTorch models. And now let's talk a little bit about the architecture. So internally, DeltaTorch is built on top of the Delta Rust standalone Delta Lake implementation. So DeltaRS heavily utilizes PyArrow for working with Parquet, and basically, as I mentioned before, we are using ID column to shard the data. So how it might, go back, how it might look like for the single GPU training. We have just one PyTorch process which sees the whole data table, and we have two. Of course, if you configure two workers, so we have two workers which are going to simultaneously read different portions of the table. So in our case, we will actually split the table in two parts, and the first worker will read the first part of the table, first half, and the second will just read the second half. And we will use the ID field for that. And internally, PyArrow might use also threads. And in the case of distributed training, in the case of DTP or FSDP, we will have multiple ranks. Those ranks might run on one node, or they might run on multiple nodes. That does not change anything. Each ranks will know own bounds, the min and max ID, and then it will divide it into the two parts for two workers. That's our example. Of course, you can configure 4 workers with multiple ranks. So then each worker will know own part and will just read the own portion of the data. And then we can also have the shuffling of the data within each rank and worker, right? So for each row group, we will have, or in reality, it's not row group, for each row batch that PyArrow will give us, we will have the shuffling. And now a bit about performance. So as I mentioned, I have I have tested the performance against Storm, and we can see that on DeltaTorch we can roughly scale in the same way, but we are using less memory. And we can we also run faster. So it's not 2 times, but it's kind of almost 2 times faster if compared to Storm. And that's the test I have conducted on AWS with 2 machines of G5 family. And so G5 is using 810 GPUs, and we have used ImageNet for that data set. And as you can see, it scales nicely with up to 16 GPUs. As I remember, 16 GPUs means 4 nodes, 4 GPUs on each node. And now let's see the demo. Okay, so let's start with the really small demo. So here we will be working with the Caltech dataset, and here is the data preparation code. So we will just utilize Caltech class, which is part of the PyTorch, I believe. Yeah, it's part of the Torch Vision dataset. And then we will just multiply it 10 times, and we will write it out as the delta. So here you can see how we write it out, and basically we just materialize it as a delta dataset, and we create our ID column. And by the way, that's how you can easily create ID column with a simple row number function. And now we can also do the optimization. Optimize is also available in open source Delta. So we have one optimize, and we can see that we have 300,000 rows. And that's how our dataset actually looks like. So we have our image encoded as binary, we have the label, and we have the ID. Now let's go into the main dataset, into the main notebook. Here we will use PyTorch Lightning with Torch to the O1, and we will need to build our package. And what we do next, here is our train path and the test path. We can see how many numbers, how many rows we have. By the way, here we can also look into the history. So that's how the Delta history looks like. We have here a bunch of versions. Actually, we have 11 versions. And we can also see some metadata about those versions. And you can basically use those version numbers. You can specify them in the create data loader function. Now let's look into our data model. So that's our data model. And the most interesting part is here. Here we are using create part of PyTorch data loader. So we are passing the path, right? We have the ID field, we have field specifications. We say that we'd like to shuffle, and we have the batch size, and we have the version, right? And here, that's how we actually, that's how we can call. So that's how we can create our data loader, and basically that's it. So we have our simple model, which is based on, I believe, MobileNet version 3, and on top of that model, we just pack another fully connected layer, and that's basically the standard steps. An interesting part is how you can get your data back. So DeltaTorch itself returns a dictionary. So it's called batch here. And we just have both fields in this dictionary, so you can access the fields using the names, and that's like our X and Y. You can have also 3 fields, 4 fields, as many fields as you want, and then you can use them in any way with PyTorch. And that's how you can run it in a distributed way. So we will use here a SparkTorch distributor. So that's our distributed function. So we just specify the trainer. We have a bunch of callbacks. And we also create our Delta data model. And then we can just call trainer.fit. So let's run it. And let's see how it's going to work. So that's how we use Torch distributor. It's part of the open source Spark. And you can easily, if you have already your cluster with GPUs where Spark is already available, that's the easiest way to run the distributed training. So we say that we would like to have 4 processes. In my case, I'm just using one machine with 4 A10s with G5 24x large. So I say local mode true, use GPU true, but in reality, you can say local mode false if you have multiple nodes. And you can easily use the same code, like without changing anything, to run it in a really distributed way. So while it's starting, let's look, okay, I think let's open terminal and let's look into our GPU utilization. Let's use NVI top utility for that. And as you can see, our utilization looks pretty nice. And of course, we can also play with the batch size to make it even better. But I think it's quite okay, even in this way. Okay, I believe I don't have time for another demo. Sorry for that. So maybe we should now look into the questions. So let me get back to the slides. Basically, what we have looked into today, I have introduced the DeltaTorch project for you. So here is the URL. Please open it in your browser, see the examples, and you can start using Delta tables for training with PyTorch today. And also, we are looking for the contributors. There are a bunch of issues already there, and we are also, if you would like to add some additional features, definitely feel free to create, to open APRs, feel free to open new features and submit your pull requests and testimonials. If there are something, let's say, not working, we will be happy to fix it as well. So as I mentioned, we are looking for the contributor. Thank you very much for your attention.
Awesome. Thank you so much, Michael, for that awesome presentation and demo. We do have a question here coming from our Cora on YouTube. So, can create PyTorch data loader take in table name instead of path? And to clarify, the table name refers to the name of our Unity catalog.
Yeah. That makes sense. Yeah, that's a great question. That's not there yet, but we are working towards bringing this feature. So right now it accepts paths, and since you're already on Databricks and you're also using Unity, we have a nice feature called volumes. So with Unity Catalog, you can create a volume, and you can also give people permissions for those volumes. So if you have a use case where you don't want to share your data with everybody who has access to the workspace, so you can create a volume backed by Unity Catalog, and then you can use this path with DeltaTorch. Another approach, if you are using unmanaged table, then you also have your path, and you can also pass it here. But we are going to bring the direct support for Unity tables. That's a really good point.
And our Cora has a follow-up question. How does the shuffling work under the hood for really large data sets?
Yeah, another great question. So we are shuffling within the record batch, which roughly corresponds to a row group. So within this row group, we are automatically shuffling the data if you turn it on, but we are not shuffling the data globally. So that might be a small limitation, but usually, like in reality, I don't think it's a really big limitation for a big data set, because if your row group is already quite big, it's already like you already have your shuffling within the record batch.
Excellent. And another question for you, Michael. Is there support for TensorFlow, and will there be in the future?
Yeah, that's a good point. We hear it from time to time. So right now we don't have support for TensorFlow, but I have mentioned we are looking for the contributors. So it would be great if community can help us with that. We see that PyTorch we have well, maybe at least that's what I see. From my perspective, I think we have a really good PyTorch adoption, and people are now using PyTorch a lot. Because of that, we have created the PyTorch implementation first, but TensorFlow is still really important. So it would be great if the community could help us with the TensorFlow implementation, because we can use exactly the same approach and the same building blocks for the TensorFlow, and we have abstract classes which can be directly used with TensorFlow.
Excellent. And Data Pipes API, does DeltaTorch support this, Michael?
Yeah, that's another really interesting project which were introduced by PyTorch a couple of maybe even, I don't know, it's maybe over a year ago. So we had the support, but I think now it was dropped, but I think we will bring it back. So it's really nice API. I really love how PyTorch really implemented that. We will add that as well. So why data pipes might be important, because with data pipes, after, for example, you get a DeltaTorch data pipe, you can implement something on top of that before you actually push it to data loader. So it basically gives you more, opportunities to do some specific data transformation. So we are really going to bring that back. And if there are somebody willing to contribute that would be great as well. That's also another small project which can be contributed.
Great. And If anyone has any final questions for Michael, we have about 5 minutes left in today's session. Feel free to place them in the chat here. And Michael would be more than happy to answer those. Looks like you answered everything from YouTube, Michael, and LinkedIn. Awesome.
Awesome. Thanks, everybody.
If there are no other questions, that will bring us to the end of our first ever session of Delta Lake Deep Dives. Thank you so much, Michael, for taking the time to show the community the power of bringing together Delta Lake and PyTorch. For those of you that would like to revisit the insights from today or share it with colleagues, the full recording of today's session is available on the Delta Lake YouTube channel. I highly encourage everyone to subscribe and stay updated with Delta Lake there. You'll be able to see all of our future deep dives as well.
Thank you for having me.
Excellent. Thank you for everyone that joined us today. And with that, we will end today's session. Thanks again, Michael.